Thank you very much. Welcome, everyone. It's a pleasure to be here today. As Dr. Schaefer said, you can call me Bob Kirish. I'm the chair of biomedical engineering at Case Western Reserve University and the executive director of the Cleveland FVS Center. I'm just going to say a few things about the FVS Center. We're funded by the Department of Veterans Affairs, but we're really a consortium of the VA, Case Western Reserve University, Metro Health, University Hospitals, and the Cleveland Clinic. And we have investigators from all those places. If you want more information about the FVS Center itself, I just put the web link up there. We have a lot of people. We have 87 investigators, more than half of whom are clinical physicians and therapists. Our mission is really to transform rehabilitation, to change the way that it's done. We identify needs, we understand the mechanisms, we develop technology to address the deficits, and then we work very hard to translate these into treatments that improve clinical care. We have 5 research thrusts. I'm going to be talking mostly about movement restoration today, but we also do pain mitigation, autonomic restoration, brain health, which is many different things, stroke and epilepsy, Parkinson's disease, et cetera. And we have now a translation and clinical dissemination core as well. We apply this to many things. This is really as I'll say in a second, the nervous system controls a lot of things, and things can go wrong, and we can use electrical stimulation, which I'll describe in a second, to treat many of these. This is a list of applications of functional electrical stimulation. And as I indicated, we really try to have clinical impact. So we do a lot of first-in-man implementation of treatments. Okay, just a couple of words about functional electrical stimulation. It's pretty relevant to my talk today. Just about everything in your body is controlled or influenced by the nervous system. And functional electrical stimulation is the use of small electrical currents that we can apply appropriately to either activate or inactivate neural circuits. So if we can do that correctly, we say FVS, functional electrical stimulation, speaks the language of the nervous system. We can interface with the nervous system at many different levels, from nerve branches, peripheral nerve trunks, spinal cord, and brain. Like I mentioned before, we have techniques to activate the nervous system and inactivate the nervous system. We have optical techniques that are being developed. We can apply this to both motor and sensory systems and to things like neuromodulation. That's just a repeat of what I showed a minute ago. Okay, so that's kind of my intro. Now I'm going to talk about one of my own research projects. And this picture here shows the concept of what we're trying to accomplish. This gentleman, you could say, you could imagine, has a high-level spinal cord injury. So cervical 1 to cervical 4 levels. That means he's paralyzed really from the neck down mostly. And typically have pretty impaired sensation and very limited rehabilitation options. So that's the group of people that we're going to be working on today. This guy, it shows him as having an implanted functional electrical stimulation system. And the idea of this is it applies stimulation to the muscles throughout the shoulder, arm, and hand. And it causes contractions of the muscles that power movements. And if they're coordinated appropriately, you can do functional activities with stimulating these muscles. So this is the FVS system that I just described. I've worked on people with these high-level injuries for quite a long time now, and we have tried many, many, many different ways of giving them the ability to command the movements that they want to have happen with their arm and hand. It's not a trivial task. There's many motions that have to be commanded at the same time. they have very few sources. So we've looked at things like voice recognition and eye movements and head movements and tongue movements and many different things. They all work in a very limited way. And so we have transitioned a number of years ago to recording signals from the brain that are related to movement intention and using that to control the person, or to give commands to the FVS system to allow the person to control their own movements. Okay, so this is where we're trying to get. It says their intuitive control of FVS powered arm movements. That's the goal. This is where we the rest of my talk is going to be basically about where we are right now. This system is what we've implemented in the recent past. This is, I'm calling it prototype 1 because we have 2 prototypes, and I'll show you the second one near the end. In this case, the FVS system is not fully implanted, but the electrodes are implanted in the muscles. They're percutaneous, so the wires come out through the skin. And we implanted these percutaneous electrodes in quite a few muscles of the shoulder, elbow, wrist, and hand. And there's an external stimulator, which is here. That's the FVS system. This is a tried and true method of stimulating muscles in kind of a prototype system. On the brain level, we use what's called brain gate. And this is we partnered with people at Brown University and Stanford University, Massachusetts General Hospital. And if you look very closely here, there's 2 little tiny rectangles there. Those are electrode arrays. They're implanted in motor cortex in a person's brain. I mean, conveniently located right about 1/4 inch below my finger, right on the surface. And then there are, when we're doing testing, there are sort of head stage amplifiers here that amplify the signals and send them to an external computer, which relates the firing rates of the axons that we're recording from, the neurons that we're recording from, and translates them into movement intention. Okay. So I described this already, but we have about 192 of the musical accompaniment even. The electrode arrays in the brain, there's 2 of them. They're each 96 channels. So we have 192 recording electrodes. All the processing then is external. So what I'll say it down here. We had 36 percutaneous intramuscular FVS electrodes, and the stimulation system is also external in this case. So we called this a fully functional reversible. It's a dress rehearsal for what we eventually want to get to, which I showed in that earlier slide. This was really a way of testing the system out without making a permanent implantation. These are the brain electrodes here. This array is 4 by 4 millimeters. The electrodes are 1.5 millimeters long. The length. The tips are exposed to allow the recordings. The electrode arrays are, as I said, implanted in motor cortex. There's a wire bundle, which is shown here, goes up to a pedestal, which is shown here. And when we want to do recordings, we screw, that pedestal is bolted to the skull and goes through the skin. When we want to do recordings, we attach a cable to it. Okay, this video shows basically the whole idea of the study. So this gentleman is our first participant. You can see the head stages here that are attached to his pedestals. They go back, these cables go back to an array of devices that amplify and condition the signals and then do the translation. So we're recording individual action potentials and some continuous electrical signals from the brain. We convert that into intended movement. I don't really have a lot of time today, so I'm not going to go into that. But The output is, these are intended movement velocities, in this case for the hand aperture, opening and closing the hand, and the elbow angle. So he's thinking about making movements, and we're recording those signals, and then we're converting them into what we hope are those movements, commands that generate those movements. Now, what he's doing here is he's wearing 3D glasses. There's a 3D display that you can see there. It's kind of fuzzy here because of that. There's a, we call it a ghost arm pops up. It's really hard to see. If you look, you might be able to see it. He's trying to match the position of his elbow and his hand opening to that ghost arm. He's very good at it, by the way. So we decode these signals. We get these intention, the movement intentions, which then in this second panel from the top, we relate that to the muscle activation patterns that are needed to generate those movements, which we've also predefined. So those dotted lines going back and forth here, oops, right there and there, they correspond to the up and down movements on these traces. These are different muscles. These curves are different colors, and it basically says I want the pulse width to be somewhere between 0 and 200 microseconds, okay, for different parts of the movement. Down at the bottom, the gray boxes that pop up are the targets. So these are the hand and elbow angles that he has to match. These are measurements of his actual movements. So you can see it turns gray. He eventually moves it down into there, and that one too, and then it turns green. So he's able to make these movements. Now, the key here is, even though we're displaying all this stuff on the screen, he has to actually, his movements are actually being generated by stimulating his muscles. You can see his arm and hand moving here. And that's, so the visual targets are there to help him. This is an early experiment to understand what the task is. But he's actually doing the task because we're stimulating his arm to do that movement. Okay. Just very quickly, I'm not going to go into great detail, but this is success on the various tasks, the elbow, wrist, hand, and shoulder, different repetitions of that. He can hit the targets when we ask him to do one joint almost every single time, 100%. Okay, so it's very close. There's a few that are a little bit less. When we ask him to do 2 or 3 movements at a time, that starts to go down, that success rate. So for example, this is elbow and hand, and you can see that there's a few of them up here around 100, but a lot of them are below. Elbow and shoulder, elbow and wrist, elbow, wrist, and shoulder. So there's a decrease in sort of the ability to control things simultaneously. You'll see that in a video in a second. Okay. He's also, his movements are better when he's actually doing a virtual reality task. So you can tell that his commands are pretty good. So he starts here in the middle, and he's moving to various targets in his workspace. Okay, they're shown here. And the movements themselves go directly to the target in almost every case. And they're almost lines, just like able-bodied people would do. When we use the FVS, it's a little more, it's less beautiful. Let's just put it that way. He makes a lot of those targets, but they take longer, and he tends to do it one joint at a time and not straight to the target. Okay. So this is our first attempt at doing sort of giving him less help moving to targets. So an engineer that works with me for a long time, Bill Memberg, is giving sort of visual and oral comments about, close your hand, open your hand, extend your elbow. Again, remember, this is all being done by stimulating his arms. He's completely paralyzed. So he's able to follow these commands, these prompts, these sort of less specific prompts. All right. Then we moved into, I'm really going fast here, I'm sorry. We moved into more functional tasks. So first of all, notice that he goes up and then in. So he's dividing, he's not going straight, he's not bringing it straight up to his mouth. Also notice that even though he struggles a little bit here with his trying to get that straw in his mouth, it doesn't mess up the rest of his movement. You know, the face is pretty close to the hand and the motor cortex, and you might expect that to do that, but he's able to separate them. The other thing to notice is that the cup is around his thumb, but his thumb is, he's voluntarily grasping that using his commands. So it's not, we don't have him glued or strapped to that cup. Okay, so we asked him what one task would you like to do that you can't do now? And he said, eat mashed potatoes. So there they are. You can see he can, again, he's using a modified fork, but he's holding on to it. He digs it into there. Again, he goes up first and then he brings it in and he eats the mashed potatoes. Okay, so he'll do it again. This was a big deal for him and for us actually, but kind of a tearjerker to see him doing this. Again, he's been paralyzed for something like 12 years at this point, and he's feeding himself. Okay, so that's prototype 1. Okay, so we've since moved on. We've enhanced our system quite a bit, and that's what I'm going to describe in the time that I have left, which is how long? Do you know, Byron? Can you tell? Perfect. So prototype 2 was the title of my talk. It's called Reconnecting the Hand and Arm to the Brain. And we've specifically named it rehab because we're going for functional outcomes here. And this is an outline of what we're doing in this study. So it's still ultimately a percutaneous system, but we've made major enhancements to both the brain interface and to the FVS system. So I'll start with the brain because it's on the top here. Instead of 2 electrode arrays that are in motor cortex, we implanted 6. They're a little bit smaller, each one. The ones that I showed you before were sort of 10 by 10. These are 8 by 8, so there's 64 on each one. But we implanted them in different areas. So we have 2 of those still in motor cortex. We have 1 in a parietal area. We have 1 in a frontal area, and we have 2 in sensory cortex. And that's for stimulation to provide tactile sensation and some feedback control possibilities. So we now have 64 times 6, which I think is 384, recording or stimulating electrodes in the brain. And I'll come back to why we chose those areas in a minute. The FVS system, instead of being individual intramuscular electrodes, we put nerve cuff electrodes around basically all of the major nerve trunks of the upper extremity. And they're listed over here. Yeah. So basically all the ones that control the hand, the elbow, the wrist, the shoulder are included. And those are these little blue cylinders shown on the nerve up here near, in some cases, very close to the brachial plexus. They're all quite high up in the arm. Okay. So the goal here is, instead of having to select some subset of muscles to try to produce movements, is to have access to basically all the muscles of the arm and hand. Okay, this is our team. You might recognize some of, if you're from University Hospital, some of your neurosurgery colleagues. Jonathan Miller is the sponsor investigator of the IDE, for example. Dr. Kumar is a plastic surgeon, and Jennifer Sweet is another neurosurgeon. Anyway, I'll refer to these folks. The real driving force these days is Blue Ajiboye. Okay. So our FVS system, we're using what are called C-fines. They've been used in other applications in other ways. They've been used in the lower extremity. They've been used for restoring sensation in amputees. But these are 16 contact nerve cuffs, and they kind of fold around the nerve like a book. So most nerves, peripheral nerves, look like this. They have kind of a flattened oval shape. They have number of fascicles in each one of the nerves. For the nerves that we have, there's not quite that many fascicles, but the idea is to get fascicular level selectivity in the stimulation so that we can activate different levels of muscles. But you can see that this folds over and it wraps around the nerve. So you have 8 contacts on the top and 8 on the bottom. This is the work of Dustin Tyler. I'm not going to go through this in any detail, but this shows the nerve that we place these nerve cuff electrodes on, and the muscles that they innervate, and sort of the activation that's expected. So this was designed to provide activation of basically all the muscles in the upper extremity that we need for movement. And we've done one participant not too long ago. You can see, well, it's hard for me to see this, it's small, but you can see some of the, there's one right there of the nerve cuff electrodes. The things that look more like screws are, they're connectors. So that it's in the future, if we have an implanted stimulation system, we can disconnect the percutaneous interface and connect to the leads that go to the nerve cuff. And these are some of the leads coming out from this individual. This is fairly early on, but that has worked out very successfully. When we want to do stimulation, we just connect these to our stimulator, these connections. He has a total of 118 nerve cuff contacts that are on these nerves. Okay, so our results are very qualitative and general and new. We basically focused on, does this system provide us what we want? And then we have a bunch of studies that are starting, but I'm not in a position to present them today. These are a few of the main nerve trunks that we're stimulating. And basically what this shows is if you stimulate axillary nerve, you get deltoid contractions. That's what we want. The radial nerve does a lot of different joints, and they show up. Ulnar nerve does a couple. It's largely sensory. The median nerve does what you would expect it to do, and the musculocutaneous nerve does what we expect it to do. These are the different contacts. There's 15 contacts that are used. One of them is the return, the common. So we can generate movements like we expected. Our participant actually has some sensation. So we stimulate through the nerve cuff contact. So we can also get some perception of tapping, of tactile sensation. So we, just by stimulating those nerves, we can get some on the index finger and some on the thumb, and also in the various places in the forearm. Okay, I'm getting close to the end here. I'll just tell you where we place these electrodes in the brain. Primary motor cortex is really sort of an execution muscle-like commands that we're sending out to the periphery. It's the last output from the brain for movement. That's what we've done and others have done pretty extensively. We also added right across the sulcus there, the corresponding areas in sensory cortex. We're hoping to evoke tactile sensation and also use it to help motor control, subconscious motor control, by knowing if their finger is making contact and how hard. They can automatically change their motor commands. And we're hoping to do proprioception. It's much more difficult to, it has proven to be more difficult to obtain so far, but we're going to give it a shot. The anterior interparietal area is a little bit further back in the brain. It's more related to sort of geometry. Where's your hand in space, and where's the object that you're trying to obtain in space? So it's the relationship between those two, a little more abstract and a different sort of modality than just the motor commands to the muscles. And finally, we put an array in the interior frontal gyrus right next to Broca's area, but we did mapping during the surgery and avoided Broca's area. This is really more cognitive in its intention. This area is well known to be related to, that's what I want to do. I want to do this task, and there's the object that I want to obtain. So it's even a higher level of abstraction. So our work right now is to figure out how to piece these together. There are different aspects of movement. We think that's an advantage. How we integrate those, we still need to demonstrate. We did do a surgery. This is these are the different arrays. There's one here, and this is the frontal area, 2 M1s, 2 in S1, and 1 in AIP. These are the 3 pedestals. When, a couple months later, this is what it looks like. Looks pretty clean. The head stages, we have new head stages that are much smaller and more manageable. So experiments are underway to utilize these this new system. So in summary, I think we've shown that we can use functional electrical stimulation to power arm and hand movements. We know how to do that. The brain-computer interface can command upper extremity motions. We're trying to improve that, but it's clear that that can happen. In our ongoing study, the rehab study that I just described, we have additional brain areas for recording. We're doing some stimulation in the brain for sensory restoration, and we've greatly expanded the number of muscles that we can activate in the periphery to power those movements. So thank you. It might look like that by now. So I'm open for any questions if there's time.
Any questions for Professor Kirish?
Isolating the nerve trunks.
You mean,
Repeat the question.
Oh, she asked, how are we isolating the nerve trunks? Well, I'm not a surgeon. So, basically it's a surgical procedure. We stimulate the nerve that we think is the right one, and to make sure we have it, and then they place the nerve cuff around that and run eventually we run the leads through the skin many times, 118 times in this case.
How many total patients have you done so far?
Here in Cleveland, we've done 2. You saw them. Well, yeah, you saw both of them there. We have been part of a consortium where we worked with a number of other ones as well. We obtained our investigational device exemption just a couple years ago. The pandemic didn't help us very much. We're supposed to do 4 of these, and we're behind, as you might imagine, because of that.
We understand that.
We did do our second surgery last winter, so I think we were one of the first ones to get back into the game. But yeah, we were delayed a long time, more than a year. Okay.
Well, thank you very much.
Yep. Thank you.